Hi, I'm Swapnali, a fourth year undergrad in the Department of Electrical Engineering at IIT Madras, and today I'll be summarizing the course Introduction to Photonics EE5500 taught at IITM. So, before we get started, it's important for us to know why we should be studying photonics or why it is a field that is important. So, photonics is used in virtually every industry in our lives today, ranging from communication, medical imaging, renewable energy, manufacturing, cameras, and quantum computing. Communication is the most widespread use case where most of the optical fibers that we use for our high speed internet and telecommunication are are an application of ray optics, as we'll see. Medical imaging, photonics is applied in techniques like optical coherence tomography and laser induced fluorescence. These technologies provide high resolution, non invasive imaging, so that helps in diagnosis and monitoring of various medical conditions and diseases. Then renewable energy, so solar cells are one of the biggest sources of renewable energy today, used today. And the photovoltaic cells which are used, which convert sunlight to electricity, are an application of the concepts of photonics. um, Coming to manufacturing, so photonics is also used in manufacturing processes for precision and control. So in technologies like 3D printing or cutting, welding, engraving, sometimes traditional methods are not as precise as we would want them to be. So using photonic lasers allows us a higher efficiency and precision for fabricating intricate components. Then our phone cameras, so we use our phones every day, and taking great camera photos has been one of the biggest technological innovations, which has been aided by the concepts of photonics. So um, the sensors that capture and convert light into electrical signals, which is what happens in our cameras, use photonics principles. So the advances in image sensors, lenses, and image processing as well has significantly improved the quality and capability of the cameras that we use. Lastly, I think one of the most exciting fields of research today is quantum computing, and photonics plays a crucial role in this field. So, quantum devices such as quantum gates and quantum dots, they're used to store and manipulate quantum information. And a qubit, which is basically a photon, is the quantum analog of a classical 1 0 bit in computing. And they're being explored for their potential in creating more scalable quantum computing systems. And yeah, so these are, as we've seen, it's like from our everyday devices to telecommunication to medical use cases, and some of the most cutting edge technologies use photonics principles. And so it's really important for us to be aware of how light works and how we can use this to build better devices. So the outline of this talk is going to be, we'll go through each of the theories of optics, starting from ray optics, which is the very first and most fundamental theory, then wave optics, electromagnetic optics, and lastly quantum optics. So all of these theories are, although they explore different aspects of the propagation of light, they're all true in certain cases. So uh, as we see here, ray optics is true in a narrow range of cases. Wave optics is sort of like engulfing ray optics and extends the capabilities of it, and so on. So yeah, let's get started with ray optics. So ray optics is the simplest theory of light. It says that light is described by rays that travel in different media in accordance with a set of geometrical rules, and so it is also called geometrical optics. So ray optics is applicable mainly around objects that are much greater than the wavelength of the light that we are studying. So this is applicable to all of our everyday objects, mirrors, walls, stuff like that, because the dimensions of these objects are much greater than the wavelength of light. Um, so two scientists who have made meaningful contributions to the field are Newton and Fermat. So Newton in the 17th century for the first time demonstrated that light could be separated into constituent colors, and he also introduced the concept of light being a stream of particles or corpuscles as he called them, and he also introduced the concept of a spectrum. Fermat, on the other hand, he created Fermat's principle, which states that light travels between any 2 points along the path that takes the least time, and not necessarily the shortest path geometrically. So this approach sort of laid the foundations for the laws of reflection and refraction that we will see in the future, which form most of the computational tools for ray optics. So yeah, we'll now look at the law of reflection, which is the most fundamental law in ray optics. This says that the incoming ray, the incident ray, my bad, the incoming ray of light, the normal, which is here, and the reflected ray, they all lie in the same plane, firstly. And second is that the angle of incidence, which is the angle made by the incident ray with the normal, and the angle of reflection, which is the angle made by the reflected ray with the normal, are always equal. So these are the laws of reflection. So we'll now talk about the Snell's law, also known as the law of refraction. So now we've seen how reflection works. So that is when the ray is sent back into the same medium. Now we'll look at what happens when the ray gets transmitted from one medium to another. So Snell's law describes how light waves change direction when they pass from one medium to another with a different refractive index. So as we see here, N1 and N2 are the two refractive indexes of the mediums, and the incident ray over here in the original medium is transmitted into the second medium, and this is the refracted ray. So this is what happens if we trace the incident ray over to the second medium as well, and we see that the refracted ray has deviated slightly from its original direction. So we see here, this is the formula which describes this behavior. So theta 1, theta 2 are the angles of incidence and refraction, and N1 and N2 are the refractive indices. So it says N1 sine theta 1 is equal to N2 sine theta 2. That means that if N2 is greater, sine theta 2 would be smaller. So if the ray goes into a medium of greater refractive index, then the wave would bend towards the normal from its original direction, as opposed to if it goes into a medium of lesser refractive index, the ray would bend away from the normal. So from this, looking at this, we can say that N2 must be smaller than N1, because here theta 2 is greater than theta 1. So sine theta 2 is greater than sine theta 1. That means N1 will have to be greater than N2. So this is how refraction works. One more thing to consider here is a phenomena called total internal reflection, which we will discuss later. But to explain it over here, what happens is, in most cases, when we have an incident ray and we have a refracted ray, there would be some angle of refraction. But what happens when this angle of refraction becomes 90 degrees? So the incident ray sort of comes over here and just grazes past the surface, and that's the refracted ray with an angle of 90 degrees. So that's the critical angle. So the incident angle at which the refracted angle is 90 degrees is called the critical angle. And beyond that, if we still increase the angle, then the ray would never get refracted. Essentially, it would just reflect back into its original medium. So yeah, so when the refractive index goes beyond 90 degrees, the ray would reflect back, and this phenomenon is called total internal reflection. So our sine theta 2 would be equal to 1. So that means sine theta c, which is theta critical, would be equal to n2 divided by n1. And from there we can find what the critical angle for any interface, and yeah, for any interface of two refractive indices is. So now that we know about reflection and refraction, we can explore one of the most common applications of ray optics, which is fiber optics. So fiber optics, also known as so it's the study of optical fibers which are crafted from low loss materials like silica glass, which is SiO2, and they function as cylindrical waveguides with a central core and an outer cladding which facilitates total internal reflection. So as we see here, core is the most central part, there's the cladding, and there's also an insulating jacket to protect the inner layers of the fiber from any sort of damage. Here the refractive index of the cladding is always less than the refractive index of the core. This is because, as we discussed in the previous slide, the this system has to support total internal reflection, and that will only happen if the refractive index of the other medium is lesser than the refractive index of the original medium. So over the past couple of decades, there have been remarkable advances in fabrication, which have led to minimal loss optical fibers, approximating at 0.1 dB per kilometer of loss, which is significantly lesser than what it was for copper cables. So optical fibers have become the superior choice for data communications across long distances because they have very little loss. So yeah, now that we have looked at what the structure of a fiber optic cable looks like, we can look at how total internal reflection actually happens within the fiber optic cable. So yeah, this is the diagram of a fiber optic cable. So it says that for any combination of mediums, there's an angle for which refracted light will be perpendicular to the normal, which is what total internal reflection is. And if the incident angle is greater than that critical angle, then the light would be completely reflected into the medium. So over here, as we can see, this is the critical angle theta c, and this is where the total internal reflection is happening. And so another thing to consider when we are looking at a optical fiber is the acceptance angle. So we want to find the angle through which we can send light into the fiber, and it would be reflected. So that means it would be propagated through the fiber. If the light is unguided, as it is in this case, the data would be lost and we wouldn't get any fruitful outcome. So the acceptance cone is the 3D shape in which if the ray is somewhere within this, then it would be guided through the fiber. The acceptance angle is defined as sine of theta a, that's the acceptance angle, is equal to the numerical aperture, and the numerical aperture is defined to be root over n1 square minus n2 square. We can get this expression by calculating theta c for this, and then using geometry to find what the acceptance angle would be. On calculating, this is what we get. So the numerical aperture also describes the light gathering capacity of the fiber. So as we see here, if it has a small numerical aperture, it would the light would propagate like this, whereas in a larger numerical aperture, the light would have many more internal reflections throughout the fiber. So yeah, this was about total internal reflection. Now we'll look at modes in a fiber and how different modes are sustained. Modes in a fiber. So when as we can see here, there can either be a single mode as shown here, which is called a single mode fiber, or there can be multiple modes within the fiber, so that's called a multi-mode fiber. And usually when the core diameter is smaller, then a single mode is supported, and the fiber is called a single mode fiber. But as we increase the core diameter, the fiber starts supporting multiple modes, and that might also lead to some modal dispersion within the fiber. So the mathematical constant which decides how many modes can be supported in a particular fiber for a particular wavelength is called the V number. So the V number is equal to 2 pi times uh, a by lambda naught into the numerical aperture, where so it depends on the diameter of the core, it depends on the numerical aperture, and it depends on the wavelength of the light that's being passed. If the V number is less than 2.405, this is the single mode condition, so the fiber would behave like a single mode fiber. And if it's greater than 2.405, then it would be a multi-mode fiber. Assuming that the V number is significantly greater than 2.405, we would be able to approximate the number of modes with this formula, which says it's 4 times V square by pi square. So that was about it for ray optics. So wave optics is the branch of optics that studies the behavior of light as waves. It explores phenomena such as interference, diffraction, and polarization. The wave theory encompasses the ray theory. So ray optics is the limit of wave optics when the wavelength is really small, or when the wavelength is comparable to the dimension of the object that is next to it. So this is an example spherical wave. This is the wave front. So this is how the wave propagates, and then there is a wave normal, which is normal to the surface of the wave. Um, so two scientists who have made meaningful contributions to the field of wave optics are Christian Huygens and Thomas Young. So Huygens, in the 17th century, he proposed the wave theory of light, where he suggested that light behaves as a wave rather than a stream of particles. He introduced the concept of secondary wavelets, each acting as a source for new waves, which explained the phenomena of diffraction and interference, as we will see. So Huygens' theory was one of like the initial frameworks that helped establish the roots of wave optics. And then in the 19th century, Thomas Young, he conducted the famous double slit experiment, which provided conclusive evidence for the wave theory. So in his experiment, he demonstrated interference patterns that were produced by light waves um, passing through two closely spaced slits, um, which confirmed the wave nature of light. So we will now look at a couple of concepts of wave optics, and then look at interference and diffraction in detail. In the spectrum of light, now that we know that light is a wave, it has a wavelength and a frequency, and they're related by wavelength times frequency is equal to speed. The speed of light is always constant, so it's 2.99 into 10 power 8 meter per second. And light is divided into different regions. So over here we have on the far left, which is the highest frequency, we have gamma rays, then x-rays, ultraviolet, the visible region, then the infrared, microwaves, and radio waves, which have the highest wavelengths. So as we go this way, the wavelength increases. As we go this way, the frequency increases. The visible range is between 400 to 750 nanometers, with blue on the left side and red on the far right side, extending into ultraviolet and infrared on both ends. So the spectrum of light is yeah, depending on our use case, we use lights at different wavelengths and frequencies for different optical applications. um, Now we can also now that we know that light is a wave, it can also be described with a wave equation. So the Helmholtz equation describes how light propagates, and one important constant that's introduced is the wave number, which is equal to 2 pi times the frequency divided by the speed of light. um, these are just a few diagrams about what uh, light as a wave looks like or what it means. So this is an example of a plane wave traveling through a medium, just like we'd seen before. There are spherical waves as well. So it starts from a single point, and at this point it's spherical. It extends to becoming paraploidal after a certain point, and at very far distances it almost becomes planar, because in this cross section the diameter is really huge, so it seems like it's a planar wave. So one other thing is looking at what plane waves look like in a medium. So this is a plane wave similar to this one, but when it goes into a denser medium, it compresses. This is an analog of what happens in ray optics, where the ray of light would have bended towards the normal if it was in a denser medium. This is the wave representation of that, and then it goes back to being the same this thing as before. One other way to interpret this is that the wavelength of light in this medium would be different from the wavelength of light in this medium, which is why yeah, clearly the wavelengths are different, because the refractive indexes are different in both mediums. So now we can look at interference. Interference is when two or more optical waves are simultaneously present in the same region of space and time. So the total wave function of both of them can be the sum of individual wave functions. So this is the principle of superposition, which says that you can linearly add up two waves at any point of time in and space. So this is the setup for the classic Young's double slit experiment, with two very tiny slits over here and a screen at a far off distance. So if light were merely particles, we would expect that there would be two very bright dots, and that's about it on the screen. But instead we see these patterns of fringes, of dark and light fringes, which shows that light is in fact a wave. These fringes are determined by the intensity of these fringes is determined by the phase difference. So the light that travels through each of these slits travels a slightly different path. So there is a path difference, so the distance traveled to any point on the screen by both of these light waves is different, and this path difference can be translated to a phase difference, and that phase difference means that the intensity of the superposition would be different at different points. So the points where it's the brightest, it's called constructive interference, and that's usually when the waves are in phase, and when the waves have a phase difference of pi, then it leads to destructive interference, and we have almost no light seen over there. So this is the phenomena of interference. We'll now look at interferometers, which are an application of the concept of interference. So an interferometer is an optical instrument that splits a wave into two waves using a beam splitter, and then it delays them by unequal distances, redirects them using mirrors, and then recombines them to detect the intensity of the superposition. So as we see here, these are the three most common types of interferometers: the Mach Zehnder, Michelson, and Sagnac interferometers. So for example, in the Mach Zehnder interferometer, we see light coming here. Then there is a beam splitter that splits light into these two paths. The light takes this path over here, redirected by a mirror. Similarly, one other path through here, and then at this point it's the recombined, and then it's sent into two different directions. In the Michelson interferometer, light is one beam travels this path, one beam travels this path, and then they are recombined. Whereas in the Sagnac, the beams travel in opposite directions. So this goes clockwise, this goes anti-clockwise, and then they are recombined. um, while here there is it doesn't look like the significant part difference, changing the position of these mirrors. So for instance, if this mirror is moved to the right or this mirror is moved upwards, we can introduce a part difference that would mean that there'd be unequal distances traveled by both of these beams, and then that would lead to some sort of superposition that we can use to understand the beam of light better. So Michelson interferometers are usually used in optical coherence tomography. That's a medical application. The Mach-Zehnder interferometer is used in optical switches and sensors, and the Sagnac interferometer is used in optical gyroscopes. We'll now move on to diffraction. So diffraction is a phenomena that occurs when wave encounters an obstacle or aperture, which causes it to bend around the edges and spread out. So when light encounters an opening or obstacle with dimension which is similar to its wavelength, it undergoes diffraction. This bending or spreading of light can create patterns of alternating light and dark regions, as we see here, which is known as a diffraction pattern. And so diffraction is one of the most fundamental aspects of wave behavior, which plays like a crucial role in understanding how light would interact with objects that are placed in its path. Here we see the intensity graph for the diffraction pattern. So of course in the middle the intensity is the highest, as we see, and then it sort of fades off to the sides. And so there's also this concept of diffraction gratings. So diffraction grating is like a specialized optical component that is designed to exploit the phenomena of diffraction. It consists of a series of closely spaced parallel slits or rulings that act as a source of secondary wavelets when illuminated by like a coherent light source, as we see over here. These secondary waves then interfere constructively or destructively, and then they produce a distinct pattern of bright and dark spots that we can then use to figure out what sort of a light source it was. So yeah, that's about diffraction gratings. So that was it for wave optics. We looked at wave equations and what wave fronts look like, and then we explored two major phenomena of interference and diffraction. Now we can look at electromagnetic optics, which quantifies wave optics and talks about the kind of waves that light is made of, and how we can sort of quantify the wave equations. So electromagnetic optics, it's rooted in Maxwell's equations, and it explores the interaction of light and electromagnetic waves with materials. So Maxwell was the most important contributor because he proposed a set of four equations. That the equations show that when electric fields change, they create magnetic fields, and when magnetic fields change, they create electric fields. So this discovery led to the idea that light is a wave that is made up of changing electric and magnetic fields traveling at the speed of light. So these equations not only connected electricity and magnetism, but they also paved the way for many technologies that we use every day, like radio, TV, and wireless communication. So Maxwell's equation form the backbone of most of those technologies. So this is a visual depiction of what the electromagnetic wave would look like. So this is the direction of propagation of light, and perpendicular to that we have an electric field in this plane, and then we have a magnetic field in the perpendicular plane. And a change in the electric field would induce a magnetic field, and a change in the magnetic field would induce an electric field. A few important formulas. So the speed of light is equal to 1 by root over epsilon naught mu naught, where epsilon naught is the permittivity and mu naught is the magnetic permeability of the medium. Let us now look at the actual Maxwell's equations. So let's talk about the Maxwell's equations, which are so like the quantitative form of the equations that Maxwell proposed. So in free space, these are the four equations which relate how electric field and magnetic field interact with each other. Uh, a part of these equations were introduced previously as laws. So this is Ampere's law, Gauss's law, and so on. But Maxwell unified all of these into a theory of electromagnetics that explained overall how electric and magnetic fields interact with each other. Uh, these laws change a little bit when light travels through a medium. So that's because the medium has some amount of polarization and magnetization, which would cause changes to how the medium behaves. As we have already seen in wave and ray optics, the behavior of light in a medium is different from what it is in free space. So, for any sort of mathematical calculations of what the wave of light would electromagnetic wave would look like, we can use Maxwell's equations with the boundary conditions that have been described in the problem statement to get to an answer. So that was it about Maxwell's equations. These equations are also used extensively in a lot of applications, real world applications where we need to be precise and exact. So now we'll move on to the polarization of light. So, yeah, polarization of light, it refers to the orientation of electric field vector in transverse electromagnetic wave. So it can be the polarization can be of many types. It can be linear, it can be circular, it can be elliptical. So elliptical polarization is essentially when the two amplitudes are not the same, so it's not circular anymore. And linear polarization is a different type. So the polarization of a particular light wave can also be changed if we want to. So there are devices called wave retarders which delay a particular component of the wave, and so they might change the polarization. So two common examples are the quarter wave and half wave retarder. So the quarter wave retarder delays it introduces a phase difference of pi by 2, and it changes a linearly polarized wave into a circularly or elliptically polarized wave, and vice versa. Whereas a half wave retarder leaves the nature of the wave the same, so a linearly polarized wave stays linearly polarized, and a circularly or elliptically polarized one stays the same, but it changes the direction. So a left circularly polarized wave turns into a right circularly polarized wave, and so on. So yeah, so that's about wave retarders. There are many other polarization instruments as well that help us change the polarization of light, and this can be used in many technologies. So that was it for electromagnetic optics. Maxwell's equations and polarization are two of the most important concepts. We will now look at quantum optics, which is one of the newest theories of light. Let us now move on to quantum optics. So, from a quantum perspective, light consists of particles called photons. A photon is a unit that carries electromagnetic energy and momentum, and it also carries intrinsic angular momentum associated with its polarization properties. A single photon has zero rest mass and it travels at the speed of light in vacuum. So, two major scientists who made meaningful contributions to the field were Max Planck and Albert Einstein. They were pivotal figures in the development of quantum optics. Um, Planck's work in the 19th century was that he introduced the concept of quantized energy to explain black body radiation. So he proposed that energy is emitted or absorbed in discrete units or quanta rather than in a continuous manner. Planck's quantum hypothesis also opened the door to a lot of new research in the field of quantum optics. Secondly, Albert Einstein, who built upon Planck's work, he made a groundbreaking discovery about the photoelectric effect. So he proposed that light consists of discrete packets of energy called photons, and he suggested that when light interacts with matter, it does that in quantized units, and the photoelectric effect can be explained if by the emission of electrons from a material when it absorbs a photon. So these two discoveries were one of the initial works in the field of quantum optics, and that's what the rest of the field has been based on. So now we'll look at a photon in greater detail. So the most fundamental unit in quantum optics is the photon. So the energy of a electromagnetic mode is quantized to a discrete level separated by the energy of a photon. That means that any electromagnetic mode, any two modes, the difference in energy would be some multiple of the energy of a single photon of a particular wavelength. So the photon's energy is the most fundamental unit, and yeah, is like the most fundamental packet of energy. And if energy has to be added or removed from any mode, then it has to be done in units of photon energy. So the energy of a photon is given by h times nu. So h is Planck's constant, which is a universal constant, and nu is the frequency of the photon, and E is the energy. On simplification, we can say that the energy in electron volts is equal to 1.24 divided by the wavelength of the photon in micrometers. One other place where this is applicable is atomic energy levels. So for instance, if this were atomic energy levels, then when there is a transition of an electron from, say, the fourth energy state to the ground state, it would emit a photon. One electron would emit one photon, and the energy of that photon would be equal to the energy difference between the fourth state and the ground state, and so on. So yeah, now we can look at how photons interact with matter. So photon interaction. So if photon energy matches the atomic energy level difference, then an atom may emit or absorb a photon by undergoing downward or upward transitions between its energy levels. So there are three forms of interaction possible: absorption, spontaneous emission, and stimulated emission. So in absorption, this is what it looks like. So you have a photon which hits an electron. The electron absorbs this photon, and then it moves to a higher energy level, and the difference between energy of these the difference between energy of these two levels would be equal to the energy of the photon. So this is absorption. And emission is when the electron loses energy to come to a lower state. There are two types of emission: spontaneous and stimulated. Spontaneous emission is when the electron spontaneously loses some energy in the form of a photon, and it goes to the lower ground state. Whereas in stimulated emission, another photon sort of triggers this electron to go to the ground state and release two photons of the same type. So this can lead to a cascading effect later, because these photons can go and trigger the production of more photons, and so on. So yeah, this is how these are the three ways of how a photon interacts with an electron. Now we look at the applications of absorption, and then come back to spontaneous emission and stimulated emission as well. So absorption is used in the phenomena of absorption spectroscopy, the technique of absorption spectroscopy. So absorption spectroscopy is a powerful analytical technique that is used to study how substances absorb light across like a range of wavelengths. When light passes through a sample, so certain molecules absorb specific wavelengths of light due to electronic transitions within their atomic structure. So the absorption spectrum, which we see over here, it is a graphical representation of this absorption behavior, and it appears as distinct peaks or bands which correspond to the energy levels involved in the absorption process. So by looking at like these absorption patterns, we can identify the type of molecules that are present in this sample, and we can also like figure out their concentration. So Beer's law, which is given by A is equal to Beer's constant into B into C, where B is the path length and C is the concentration. It helps us correlate the absorbance that we have calculated with the characteristics of the substance itself. So absorbance is given by log of P naught by P, where P naught is the power of the incident radiation and P is the transmitted power. And so yeah, so we can find the changes in concentration depending on the changes in absorbance and stuff. So this is about absorption spectroscopy. We'll now look at another technique. Talking about the concept of fluorescence spectroscopy, first we'll try to understand what fluorescence is. So fluorescence is a phenomena in which certain substances absorb light at one wavelength and then they re-emit it at a different wavelength. So when a molecule absorbs light energy, the electrons are temporarily excited to a higher energy state. As these electrons then return to their original state, they would release excess energy in the form of fluorescence, and this emitted light usually has a wavelength that is longer than the absorbed light. So fluorescence is widely used in natural phenomena such as the glow of certain minerals or also the vibrant colors of certain marine organisms. Um, Fluorescence spectroscopy, which is the technique mentioned here, it leverages the properties of fluorescence to analyze and identify substances. So in this method, a sample is exposed to a given specific wavelength of light, as shown in this setup. This is known as the excitation wavelength, and that causes the molecules within the sample to fluoresce. The resulting emission spectrum, it's a plot of emitted light intensity against wavelength, and that provides valuable information about the composition and concentration of various substances within the sample. So for instance, it's really helpful in distinguishing cancerous cells from non-cancerous cells, since they respond differently in fluorescence spectroscopy. So yeah, that's about fluorescence spectroscopy. So stimulated emission, the most common device that does this is called the laser, which is light amplification by stimulated emission of radiation. And so stimulated emission allows a photon in any given mode to induce an atom whose electron is in an upper energy level to undergo a transition to a lower energy level, and in that process it emits a clone photon into the same mode as the initial photon. So if we look at this diagram, we have a photon that's coming in and we have electrons at excited state. These electrons in the presence of that photon, they undergo a transition to the lower, let's say, ground state, and then they emit photons that are the same wavelength as the original photon. And this process goes on because one photon can trigger another electron and so on. So that's why it's called an amplifier. So one kind of lasers are optical fiber amplifiers. So they amplify they amplify signals or like light without needing to converting it to electrical signals. So one common type of optical fiber amplifier is the erbium doped fiber amplifier. It's also called the EDFA, and it's used widely in like long distance telecommunications. So EDFA consists of silica glass fiber doped with erbium ions, so that's the gain fiber here. And the core of the fiber is the amplification medium, and when it is pumped with light at a particular wavelength, usually it's around 980 nanometers, the erbium ions within this fiber absorb the energy and they release it at a longer wavelength. So usually it's around 1550 nanometers, which is a crucial window for low loss transmission in optical fibers. So the working of these optical fiber amplifiers, it also involves the process of stimulated emission, where incident photons stimulate the emission of additional photons with the same energy and direction. And in the case of EDFA, as the erbium doped fiber is pumped with light, the erbium ions get excited and then they release photons in the same wavelength range, so thus amplifying the incoming optical signals. So this process allows optical fiber amplifiers to boost the strength of optical signals directly within the optical fiber. So this is like a block diagram of the same thing. So now let us look at how a laser would work. So we know how the transition from a higher level to lower level happens in the presence of a photon, but we need to find a way to get photons to the higher level in the first place, which is what we will look at next. So population inversion is basically the process through which you can get electrons in an excited state. So the essential ingredient for achieving laser amplification is the presence of a greater number of electrons in an upper energy level than in the lower level, which is when they can like decay and come down. So this non-equilibrium of electrons being mostly in the higher energy levels is called population inversion, and we need specialized ways to achieve population inversion because it's not usually there. And this process of inciting population inversion is called pumping, which is exciting electrons from the ground state to a higher level state so that then we can use it in lasers. So there are two common types of pumping, 4-level and 3-level systems. So what happens in a 4-level system is you have the ground state and the electrons are pumped from a ground state to a short-lived excited state. This short-lived excited state, the electron rapidly decays into a long-lived, more stable level. Then there is also a short-lived state between the ground and the excited state, and the laser transmission happens between these two states. So this is where the electron loses energy and emits the photon, and as soon as it reaches this short-lived level, it immediately rapidly decays again to the ground state. So these are two intermediate states which are short-lived, but they help in facilitating the laser transmission. In the 3-level system, there's one step lesser. So the pumping happens just similarly to the previous case. It's pumped to a excited state that's short-lived, which then decays into a long-lived excited state. But then the laser transmission happens directly between the long-lived excited level and the ground state itself without the need for this short-lived level in between. Now we will look at some semiconductor optoelectronics. Semiconductor materials usually absorb and emit photons by undergoing transitions among allowed levels. So two important devices to know about is a LED and a photodetector. So the basic working of a LED involves the recombination of charge carriers, which are electrons and holes, within the semiconductor material. So when a forward voltage is applied to the LED, the electrons from the N-type region and the holes from the P-type region move towards the junction between these two regions, which is the depletion region. At this junction, these charge carriers will then recombine and release energy in the form of photons. As we see here, the photons are emitted. The energy of the emitted photons corresponds to the band gap of the semiconductor material, and so this determines the color of the emitted light. So because we can control the semiconductor's band gap, this enables us to produce LEDs that emit light across a wide range of color. So this is about light emitting devices. Now the photodetector is a device that measures photon flux or optical power by converting photon energy to a measurable form. So it basically takes photons as it detects photons and then it converts them to electrical signals, so sort of the opposite of what was happening over here. So the setup is simple. It's there's a photodetector plate over here the photoelectric effect happens. It's just a metal surface. So when the photon hits the metal surface, an electron is released because of the photoelectric effect, which is then captured by this positive terminal over here, and then there's a voltage source to complete the circuit, and then there's a current indicator to figure out how many photons were incident. So this is the basic working of a photodetector. Uh, there's a couple more types of photodetectors that we can take a look at. So starting with vacuum tubes, they're also called phototubes. So this similar to what was discussed before, a photon is incident on the metal plate, an electron is released from the photocathode, and then this electron prompts more photons to be released, which prompts more electrons to be released, and so on. And so this leads to an electron cascade where a large number of electrons are released, and they're then collected at the anode, and that completes the circuit. Another type is the photoconductor, which helps in conducting electrons that can be controlled by light. So depending on the photons incident, the photoconductor would operate by registering either the photocurrent or the voltage drop across the resistor, which would depend on the number or kind of photons that are incident. So we can add a current detector or a voltage detector to this circuit to conduct electricity. And the third type is a simple diode. Now, a usual diode is a PN junction diode, but it's also possible that we add an extra layer in between, and then it's called a PIN diode. And this usually helps to increase the size of the depletion regions to improve the efficiency of the diode. So now that we have discussed many types of photodetectors, we can look at how we can grade these photodetectors. So that there are many figures of merit which are used, but the most important ones are quantum efficiency and responsivity. So quantum efficiency is defined as the probability that a single photon incident on the device will generate a photocarrier pair that contributes to the current in the detector. So numerically we say that quantum efficiency is equal to number of electron holes pairs generated and collected divided by the number of incident photons. The number of electron hole pairs would basically be the current in the circuit divided by E, which is the charge of any electron, and the number of incident photons would be the power divided by the energy of any single photon, which is h nu. So this is the formula for quantum efficiency. Coming to responsivity, it relates the electric current that flows in the circuit to the optical power that is incident on it. So IP, the responsivity is equal to IP by P, where IP is the current and P is the power of optical power. And then we can manipulate these numerically to get a relation between responsivity and quantum efficiency that's only dependent on the frequency of light, and everything else is a constant over here. So yeah, these are some ways that we can find the figures of merit for a photodetector. So finally we'll look at optical modulators. So an optical modulator is a device that is used to modulate the intensity, phase, wavelength, or polarization of a light beam. So firstly they are classified based on so they modulate light, but we can classify them based on what they use to modulate light. So the optic modulator is when light is modulated with sound. So what happens here is there's a sound control, and there are diffraction gratings, and when light is incident, depending on the sound, the refractive index of the medium would change, and then that would lead to different diffracted and transmitted lights depending on the sound wave over here. Similarly, for the absorptive modulator, it operates by varying the absorption of light in a material in response to external stimulus, so typically like an applied voltage or something. The modulation occurs as the material's absorption characteristics change, and that affects the intensity of the transmitted light, as we see here. Coming to the electro-optic modulator, They allow for a controlled manipulation of light using electrical signals, so we can vary the phase, amplitude, or polarization of light by changing the electric signals associated with it. So this was it for the summary. So we started with looking at why photonics is important, and so we started by looking at why photonics is important and where it is used today. Then we looked at ray optics, which is one of the most fundamental theories of optics. Then we looked at wave optics, we looked at Maxwell's equations in electromagnetic optics, and finally we looked at the theory of quantum optics and certain devices that we use in our everyday lives that are a result of photonics principles. So that was it for the summary of the course, and yeah, thank you.